This is a short video about cellular automata and their use in hydrology and landscape science. My name is Josie, I'm part of the CDT at the University of Exeter. That's the Centre for Doctoral Training for Water Informatics, Science and Engineering. So what are cellular automata? They're a type of numerical model based on discrete steps in time and space. They were inspired by the way we see patterns change and evolve in nature. They were first developed in the 1950s by mathematicians looking for a way to create self-reproducing patterns. If you want to know more about the basic models, take a look at the famous cellular automaton, Conway's Game of Life, from the 1970s. We're going to use this to try and understand how the basic models work. So in a world divided into these space-time steps, the space steps are represented by cells in a grid, and this can be 1D, 2D or 3D. Most cellular automata use square grids, but they can use triangular, hexagonal or any other tessellating shape. Now how these cells act with each step in time depends on their immediate surroundings. The cell that we're looking at here is surrounded by a neighbourhood of cells, and the two most common neighbourhoods are the von Neumann and the Moore neighbourhoods shown here. So the next thing to look at is the state of the cell. A cell has different states of existence, and these change with different times. Usually the states are integers. In the game of life they're binary, so a cell can have the value of either 0 or 1, meaning that it's dead or that it's alive. Now with each time step, the state of the cell we're looking at changes based on transition rules, and these are set by the model. For example, here living cells in sparsely populated areas will generate new life in neighbouring cells, while cells that are overcrowded will die off. And so to summarise, the state of a cell at any time is a function of the state of the neighbouring cells at the previous time step. We always want to go for the simplest model, but what if the simple model just isn't realistic? The rules that we can use, these transitional rules, can be lookups, expert rules, or algebraic equations. They can be deterministic, or you can add an additional random number grid and include stochastic probabilities. By understanding this, and by using CA with other modelling tools, we can start to create simulations of our environment. From the initial sand pile CA, cellular automata have been used to model rainfall runoff, erosion, landscape evolution, fluvial sediment transport, and all the other environments you see here. I hope you understand a little more about cellular automata. Thank you for listening.